DBpedia. DBpedia is one of the biggest and more important knowledge graphs around, and has been for the last decade or so, if my memory serves me right. It has been a knowledge graph before actually knowledge graphs were a hype, or before even they were a thing. So they started scraping knowledge from Wikipedia, and to do that they used the structure in Wikipedia, and by doing that they extracted a big amount of knowledge, and they have been building on that and creating a whole ecosystem around that. And this is actually what Sebastian is here to talk about today, the latest addition to this ecosystem and how they're using it, and I guess how you can also use it. So that's it from my part, and for the rest, Sebastian, the floor is yours, and take it away.
Thank you for the introduction, George. So today I'm talking about the DBpedia Databus, in particular, a platform to evolve knowledge and AI from versioned web files. This is a particular aspect which goes into data and knowledge engineering. So it is about the engineering methodology. A part of it is about the engineering methodology behind it. So you would get some knowledge engineering details and processes here, and then about the platform which provides the tool support for this methodology. So for all of you who do not know DBpedia so well, I prepared a short introduction. So starting from the left, you can see that 2007 was this first Wikipedia extraction 13 years ago. With the 4 partners, and there was a functioning Sparkle endpoint, which is stably available publicly till today, and also linked data deployment. Then soon after, basically in the same year, there was this formation of the linked data cloud around DBpedia. Trend continues, So then there was a major boost in knowledge graph and linking research. We opened the editing of the DBpedia ontology in 2010, which was labeled a new type of psych. 2011, there was major industry adoption. So IBM Watson was built, for example, using DBpedia. Yahoo used the software. BBC included the identifier. Part was given to Unicode. Then 2012 and 2016, we extended this extraction framework to cover all 140 Wikipedias, commons, and also Wikidata. And at this time, 14.4 billion facts were extracted. In 2014, we founded the DBpedia Association, which I'm the CEO of. 2016, we were starting to tackle data quality on a larger scale. That's why we developed the Shackle web standard, which allows test-driven knowledge graph development. 2018, the linked data cloud has grown a lot. And starting 2019, we really built DBpedia into an innovation platform. So it's not really about the data set anymore, but about the connecting of the data, linked data technology, and the ecosystem. Now in the future, we kind of like raised the productivity. I'll talk about this. So there are 22 billion facts per month. This is one thing. So it's monthly releases. And we have this huge linked data derived open knowledge graph. So we kind of like increased the speed of integration very much and are able to produce these huge knowledge graphs. And also we started to do fair linked data. So fair, most of you might know it, but it means findable, accessible, interoperable, and reusable. And I'll talk about these developments in 2020 on the next slides. So what does fair linked data mean? FAIR originally comes from a scientific consortium. So there are guiding principles for scientific data management and stewardship. Personally, I always wondered these guidelines, they are very vague, high level, idealistic, also altruistic, and not at all industrial. So what we're doing with FAIR linked data now is that we provide a practical implementation of FAIR. So there's lowered effort because you can reuse the implementation. We have measurable automated FAIR tests, so you can be sure that your data is fair. and the whole thing is industry driven. Now there are many things in this FAIR guiding principles that are industrially relevant. For example, findable. There is also a marketing aspect, but also internal data management aspect that you want to find data in your enterprise, yeah, because it's very distributed across your enterprise. Interoperability is, of course, a great issue, and reusability is a great cost saver. Accessibility goes along with privacy concerns and who's allowed to see data. So this has a different flavor than the original FAIR guiding principles. I would like to introduce you the DBpedia Association members up to now. So we are a very fast-growing knowledge engineering and linked data lobby. Part of it is to give the visibility that DBpedia has back to the people who contributed and built it and really drive this knowledge graph adoption. I would like to answer the question whether DBpedia is academic and is industrial. This is often quite a misconception. So it's neither and it's both, because we focus on knowledge engineering, and engineering is always taking scientific methods to produce industrial output. So more on the left side, we put the academic and non-profit and public members, and then on the right side, we put the industrial members. Yeah, so you can kind of like see this knowledge engineering methodology here or process here. I'll talk about some economical concepts just to give a background motivation why we are doing this. Some years ago, we had an Align project that was supposed to align software and data engineering. We also published a book, Engineering Agile Big Data Systems. And if you do a system analysis of your data-intensive workflow, you have these three properties, which are agility, productivity, and quality. And here I plotted basically the release cycle of DBpedia in 2016 and 2020. So 2016, we had kind of like this anti-pattern. It is called data quality creep. So we were always focusing on data quality and totally ignoring agility and productivity, which means if you go into this anti-pattern of data quality creep, your releases will be delayed a lot. And this means you use agility and you use netto output, yeah, so productivity. This is not a magical triangle. Here we lost a bit of quality because, of course, we re-engineered the whole pipeline. And during this refactoring process, I think there are minor new bugs. Yeah, so we lost a bit of quality, but we kind of like increased agility and productivity a lot. So the last release cycle was 17 months, and now it's monthly, and you can really fix the pipeline better. Another economic concept is the law of diminishing returns. So if you have an economic background, you already know what this means. This measures the productivity per unit. So if you add more workers to, so it's the production factor is labor here. If you add more workers, then you at some point you're getting more productive. But then if you add more workers to it, you kind of like have diminishing returns. That means each worker is not so effective anymore. And then if you continue this, let's say you want more and more data quality and you add more and more people checking this data quality, you will even get into negative returns. The main reason here is that data quality is Pareto efficient, so there's a 20-80 rule applies, and if you increase in quantity, you lower quality as well. And also the increase in quality makes it harder to find errors here. So as a take-home message, if you ever print the slides, you can cut this out with the scissors. If you want, you should always try to tackle data quality issues with innovation, not with more community or workforce. Yeah, so because if you double the size of your data curation community or you have more edits or more activity, it doesn't mean that you're more productive in any sense. So this is basically the take-home message, and we focus here on innovation. Now I'll come to the core. I'll introduce some databus concepts and let me see. No, it's not. Databus concepts and use cases. It's intermixed, so there will be high-level concepts and also use cases and practical demos which show these. So what's the databus? Databus is a digital factory platform. The basic process on the databus is you find data, you consume data, you process data, then you republish it. This is a very minimal building block. There's this online platform, databus.dbpedia.org, and it's literally built like a data bus in your laptop, for example. So in computer architecture, a bus is a communication system that transfers data between components inside a computer or between computers. And here, of course, we're talking in the server. It was inspired by the Maven repository, Steam, GitHub, and also the apt package manager on Linux. So these are all software deployment systems, and we focus here on data consume and deployment. What you do with this basic building block is that you can build networks and not a static pipeline. So as soon as you build pipelines and really hard integrate the, let me see another question. As soon as you build hard pipelines, you lose a lot of flexibility and agility, and you cannot test the individual data output. So what you see here is that the metadata on the top blue line is the data bus. You query the metadata for the files, and then you download the data from somewhere else. So it gives you kind of like the location of the files on the web, and then you can load it into your data cleaning service, into a service, into some sort of model, and you produce output data, and this output data you can upload the metadata on the data bus again. So it's basically orchestration of input and output between software. So how can you imagine a digital factory platform? On the right, you see a warehouse with a lot of boxes. You kind of like need to know what's in the boxes, where they are going, which box you need. So the boxes here are files. So it's a registry of files on the web, which means that any files reachable via HTTP can be described with this metadata. Doesn't matter whether it's RDF, XML, JSON, TPF. It's decentral storage, and the central metadata index is available via Sparkle API. So there's a knowledge graph as well. Right now on the public platform, there are 130,000 files and 2.6 terabyte. And you can download all of it, so there's no restriction. It's all open. It's open data. Maybe you don't want all of it, then you need to select it and drill down with the Sparkle API. And it's also a fair implementation. So if you publish files on the data bus, we guarantee that you follow the FAIR principles. So what is the core of it? There's very strict metadata. So this part is very well checked. So provenance, we allow users, organizations, and agents to publish data. And of course, you have data sets, source data sets. When your data set is derived, you can link to the source data sets. Yeah? So this provenance, there are machine readable licenses is required. Everything is signed with a private key and the X509 certificate. And we have dataset identity and versioning, which is a bit different from DCAT. So there's a gap in the DCAT standard. Here, the dataset is abstract, and then each version, you have versions per dataset. Yeah, so I'll show that in the next example. So structure, like the links are user, group, artifact, version. If you know Maven, you're familiar with this. And I'll show you one popular data set of DBpedia. So this is just a very tiny data set. So these are geo-coordinates extracted with mappings. That means from the English Wikipedia, you have a lot of, from all major Wikipedias, it extracts the geo-coordinates and put them into the file. You can see if you go on the versions that, so this is the abstract data set, yeah? And then each month we produce a new version based on the Wikipedia dump of this particular data set. You have a schema basically for the files. This is important, so you can drill down on the individual data sets. So now you just want to select the English files. And if you want to subscribe to it, there is a query generation functionality. So each month now, if you execute this query, you will get this particular new data set, just the English version of it, yeah. If you click on a version here, there's much more documentation available, and also links to the codes, and you can report errors and discuss. So there's interactivity features, and there's also the link to download the metadata. So this means you can automate these downloads totally. The next thing is, so if this gets more complicated, because we are the core collection, which I will show, it has several hundred files per month. So here, databus users can create their own data catalogs, which we call collections. So these collections are stable. They have stable identifiers, so you can put them in a scientific paper, for example, and they are dynamically updated, or they can be static. Yeah? So I'm going to show you the latest core release here, which is basically what we then load into the main Sparkle endpoint, which you all know. So here's a simple bash script to fetch the data. I hope it loads now. Yeah, but anyhow, the collection is backed by a query, which can get quite long. Yeah, so the Sparkle endpoint is quite good to handle these. And let's see. Yeah, so here you can see all the data sets. Basically, each month or each day, you can check whether there are updates to this collection, and then kind of like replicate the DBpedia Sparkle endpoint on your local machine. And you can create your own collections via if you are registered. So what can you do with the collections? There's this thing which we call, it's like rapid application deployment, because we need to maintain the DBpedia infrastructure, the core infrastructure. So as I showed before, these collections can be loaded programmatically. And if you pair this with Docker, you get a low-code application deployment. So we have this Docker image, which is a Virtuoso Sparkle Endpoint Quick Start. And here it is a 3-liner. You just feed it the collection of the latest core release. And then you start it, and you have a clone of DBpedia. And then you need to restart it, and it checks the updates for the collections. Now let's talk about, so this was the download and action part. Now I'm going to talk about this data engineering in action. So this part, I do not have detailed slides here, but kind of like, if you ask what is an application, and of course I mean data intensive applications here, so AI, search, many things that are fed by a lot of data, yeah? A chatbot maybe, or question answering systems, NLP as well. So you have an application that you are developing, and this application here always needs software and data. So these are the two components that you actually need to have a working application. Now, if you think about the software engineering part, there you have very good frameworks for it. You have Maven, you have NPM, you have the Debian package manager, you have Scala build tools, SBT, for example. And there you can really pinpoint the exact software dependencies that you need. They're recursively resolved, and you know, kind of like for each software artifact you include, you know exactly which version it is, whether there are compatibility issues, whether things changed. You have a build tool that runs integration tests normally. So there are many, many tools there. But when you think about data, so if you present your application to somebody and I would ask you, can you give me a list of data sets included and where you got them, and like a record, and what are the dependencies and everything, then normally this is done without any tools. Yeah, so, and here I see the great gap. So I prepared some homework for you also. If you compare your software engineering processes and tools with your data engineering processes and tools, so how you track data and develop data and everything, do you notice a difference? And you can think about it, and you will see that there's or I assume that you will find a great gap. Yeah, because from my experience, I was not so happy the last 10 years working with data and the tools provided to work with data. Now, the main thing also, the main incentive for us to develop the data bus is that we want to do knowledge graph engineering. Yeah? This means, in this case, it's a simple example. For us, it's a simple example, so it mainly shows the DBpedia release process. And we have this fully automated, it's in the Maven bot, so there's 55 gigabyte per release, around 21 billion triples per month and 5,000 triples per second. There's also a dashboard that tracks the process. And on the bottom, you can see the debugging, well, release and debugging workflow. So on the left top, you see that we take the time-based Wikipedia dump each month, and then there's a time-scheduled extraction. This is uploaded on the data bus. And then there is this data cleansing step, which is another component. And in the end, this downloads it and republishes it as quality controlled DBpedia release groups. What we do then is there is this large scale validation. So we run yet other tests on the final thing. And this produces reports. And here, this is the kind of like the point of truth is this community reviewing, yeah, because we just produce the data, but then it gets downloaded 600,000 times per year. And the errors are only shown in the final applications. Yeah, so if you load it in the Sparkle endpoint, if people parse it, whatever, yeah. So, and then the problem here is always to backtrack the errors and the issues to the specific component. And this is something which is possible in the data bus because we reach this unity between data package and also piece of code and software to which is responsible for this particular data part. And you can break down the tests, these data tests, you can put them into the software integration tests. So here we kind of like achieved this alignment between software and data engineering and the backtracking of the data issues in the opposite direction of the data. Now here I'm just going to show this real short. So here's a more complex knowledge graph engineering workflow. It is more complex because it's iterative, because here it's not so straightforward. So it's not pipeline like a pipeline. So the release workflow is more like a pipeline, and then you backtrack for the errors. Here, the individual components use data sets of other components, but then also improve them, and you have to reload the other components. So it's like an iterative approach. So the borders between consumption and publishing are kind of like not so linear. Yeah, it's more network-like, and this is only internally. What we're doing with this is we're deriving huge knowledge graphs from linked data. So here you can see an entity size comparison of the knowledge graphs we are building. So the DBpedia you know and you are used to is on the left side. Yeah, this is the English tiny diamond. Diamond because it's compressed data from several sources. We recently built a Dutch national knowledge graph from Dutch linked data sources. Then you have, as a comparison, you have items in Wikidata. And right next to it, there's this DBpedia small diamond, which compresses all language versions of Wikipedia plus Wikidata in one, like a diamond knowledge graph. We'll build more national knowledge graphs in the coming years, like the German one, or maybe the US one. If you're interested, please mail me. And there comes the largest diamond, which is kind of like all data sets that we integrated up to now, compressed into one huge knowledge graph that you can download. So here we increased the speed a lot. So we need right now we need around 4 hours per linked data cloud, per linked data bubble, and we are going to crowdsource this so everybody can integrate their data into DBpedia. Then we have these 2 commercial graphs, the Google Knowledge Graph for comparison. So this is log scale, and the DiffBot Knowledge Graph. And then we have, of course, the linked open data cloud, which is the largest knowledge graph on Earth. I think compared to anything else, there's more data available there, but not findable. That is a problem, yeah? So we need to bulk up the infrastructure that you can really find the particular data that you need from the lot cloud in live, and also manage the changing of the data. So now I want to show you a databus application. So previously, we focused on the consume, the download, and also developing methodology with the databus. But you can also build applications which are powered directly by the databus. And I would say this is a unique selling point because this is not possible with other data repositories. So other data repositories, you can kind of like keep or organize the files a bit, but it's very hard to build real applications on the repository itself as a platform. So this is DBP, we call it DBpedia Archival, so it's an ontology archive. I will show it real quick. So what we do is we crawl 800, so at the moment we discovered and crawl 890 ontologies, and then we do a star rating. So here you can have a list of ontologies and filter them. Maybe some audience want to see their ontology. Maybe it's we don't have time to wait till somebody suggests one. But yeah, you can try it out later how this the star rating is done. So what it does is basically this archival tool discovers and tracks all ontologies, and every 8 hours it downloads a version of the ontology onto the databus, which is persistently saved. So this means you can now use the databus to download and the ontologies and the individual versions. So if you click on, let's go for the latest timestamp to see which ontologies have been edited recently. So here, this one, you can see that here, every time a change is detected, the ontology is downloaded and persisted, and then we check for parsability. Here, for example, if you only have 1 star, then most likely the license is missing, yeah, and then a consistency check. So these are the 4 stars. So these are basically stars which are needed, so you know your ontology is fair and available. It doesn't say anything about the quality, just that you can find and access the ontology, and that it has a license attached. So there, in the backend, you have also programmatic access to download and track all the ontology versions, and this is kind of like an application built on the databus itself. Two things where I have no time, which I just want to mention shortly. So there's also a databus client, which is quite practically because it converts format and compression on download. So it's a bit different than content negotiation. Content negotiation does the conversion server side. And here you can, the client kind of like simplifies gzip to bzip2 conversion or things like that. So it's quite practical to homogenize the collections. And there's also databus mods which automate the enrichment of the metadata. So this is like, so users don't have to give something like a MIME type, because this can be automatically detected, or file size, or many other things. Void generation is done automatically. About the databus, the usage is free if you register, and we are preparing on-site deployments for the next year, beginning of 2021, so you can have a more closed architecture. Yeah, thank you for your attention. Are there any questions?
Olivier is asking if there's a user review process, and for example, what happens if you detect a bug in DBpedia data?
Okay, so this is about the data quality, yes?
I think so.
Yeah. So how does it work? So normally you would submit an issue in the GitHub, yeah. So this issue is kind of like not semantic yet, or actually the users kind of like they know already how the databus works and how to pinpoint the error. But so let's say you are not familiar with anything. You say, okay, I found this is wrong, and then you post an issue. And what we do then is we tag it with the particular artifact on the databus. So we say, in this version, we confirm it. In this version of this particular artifact, the error occurs. From there, we devise tests. So there's a mini dump where we can implement software tests. And these are in the dev branch. So in the dev branch, the tests always fail. And then as soon as one of the tests is fixed, it moves to the master branch, and then it's available next month. It gets better. So this is the overall process.
Mm-hmm. Okay, there is one that I know you're going to love because it's one of your favorite topics. So someone's asking like, okay, you know, this is such a great achievement, but how do you actually manage it? Do you have large funding, or is it because the core team is so dedicated?
No. It is really so. We have I have to say we have a very large community. I have to say so. It is still or it comes definitely from a community-based model. So. For example, Søren Auer, he manages the TB, the library now, and he gave us 3 servers. There's some hosting Mannheim, open link host domain endpoint. So everybody is kind of like contributing a bit. And we are moving, and you have to see that on the board of DBpedia, there are 6 of the top 10 knowledge engineers, according to AI Miner. So we all won a prize, basically. That we are the most influential scholars in knowledge engineering, and also our members are very much experts in the field. So there's definitely technology leadership, and this innovation helps to keep this running. And we focused the last 3 or 4 years to really make it, because before that 2 people were doing the release and they needed 12 months or 17 months in some cases. And this was very expensive, and now we automated it, so it is basically can be done by a very skilled bachelor or master student. Yeah, and this is kind of like a high cost saver, because per se the association is unfunded. So each of the members has a very huge budget. Yeah, like the libraries, the companies, the researchers. And in this funding, there's maybe always a work package included. Or for businesses, they want to show their tools with DBpedia, so there's some interest. And with the researchers, there's always a work package maybe that is particular to DBpedia.
Mm-hmm. Okay, thanks. There's actually more questions, but since we have to wrap up, I'll just do a quick one and you do a quick reply. Amir is asking, how does the star rating of ontologies work? Is it based on FAIR principles?
No, it cannot be based on the original FAIR principles, because they are too vague. So they are kind of like saying that you should have this and should have this, but they're not specifying it too much. But for ontologies, we're talking about all ontologies, which is a very small and specialized area, and there you can have clearly measurable star ratings. For the details, you have to go to archivo.dbpedia.org. We spent almost 2 weeks describing these stars, so there's a lot of information there.
Okay, great. Thanks once again for the talk, Sebastian.
Thank you very much. Bye.